This past June, at a meeting of American astronomers, a team led by Kyle Finner described something they could not fully explain. Using the James Webb Space Telescope, they had caught a galaxy cluster 10.4 billion light-years away, bending the light of galaxies behind it, and when they weighed its core, it came back denser than the standard model says anything that old should be. Not by a little. By 3.2 standard deviations, outside every simulation they tried. This is the story of the most distant cosmic monster we have ever found, and the crack it may have opened in cosmology. For a long time, we told ourselves a story about how the universe grew up, and it was a story about patience. Gravity in that story is a slow engine. It starts with almost nothing, faint ripples in a sea of dark matter, barely denser in some places than others. And it spends billions of years pulling that material together, clump into clump, galaxy into group, group into the largest bound things that exist. Those largest things are galaxy clusters. Hundreds or thousands of galaxies, oceans of hot gas, and a hidden mountain of dark matter, all held in one gravitational knot. And building one, we believed, takes almost the full age of the cosmos. So when we look far enough back in time, we expect to see clusters that are not finished yet. Loose, lopsided, still gathering. That was the rule. There is a cluster 10.4 billion light-years away that did not read the rule. We caught it in the act of bending starlight, and when we measured the mass doing the bending, the number came back wrong. Not a little wrong, but wrong in a way that reaches all the way down into how we think the universe assembles itself. This is the story of a structure that was already old when it should have been young, and why a single knot of gravity at the far edge of time is making cosmologists nervous. The cluster has an unlovely name, XLSSC 122. It was not discovered in 2026. It was found more than a decade earlier, and it announced itself the way massive clusters do, with X-rays. When thousands of galaxies fall together, the gas trapped between them is squeezed and heated to tens of millions of degrees, until it glows in high-energy light. An X-ray survey run by the XMM Newton Space Telescope, mapping large patches of sky, picked up that glow. In 2013, an astronomer named John Willis and his collaborators described it, and the description came with a small shock of its own. This was the first massive galaxy cluster ever discovered by its X-ray light at a distance this great. That distance is the first thing to hold on to, a redshift of 1.98. The light left the cluster when the universe was roughly 3.3 billion years old, about a quarter of its present age of 13.8 billion years. Astronomers call that era cosmic noon, the high tide of star formation, when galaxies were forming stars faster than at any time before or since. But it was the cluster's own stars that gave the first hint something was off. When Willis and his team looked closely, in a follow-up years later, they found that the stars in these galaxies had begun forming when the universe was only about 370 million years old. These were not young, blue, still-forming galaxies. They were already old, already quiet, already, in the language astronomers use, red and dead. And they had gotten that way impossibly fast. That was the first crack. There was more. A separate study, led by the astronomer E. Norday and colleagues, found that these cluster galaxies were not only old, but unusually compact. Dense, bulge-heavy things that had settled and evolved faster than galaxies of the same age out in the general field. Whatever this environment was, it had aged its galaxies ahead of schedule, so astronomers already held a cluster whose stars were too old and whose galaxies were too compact, sitting at a moment in cosmic history when all of it should still have been young. But every one of those clues came from the light of the galaxies themselves. The thing the galaxies were falling into, the real mass, the dark matter core, had never been weighed. And to understand why that core would become the true problem, you first have to know what the standard model swore it should look like. To feel why the next measurement unsettled people, you have to understand what the standard model of cosmology actually predicts. That model has a name, lambda cold dark matter. And for decades, it has been remarkably, almost annoyingly successful. It reproduces the faint temperature ripples in the afterglow of the Big Bang. It reproduces the enormous cobweb of filaments and empty voids that galaxies trace across the sky. It has survived test after test that could have killed it. This is not a fragile idea we are poking at for sport. It is one of the best-checked theories in all of science, which is exactly why a single cluster that seems to violate it is worth taking seriously. And that model makes a very specific promise about clusters. They grow from the outside in, slowly, and their centers take a long time to become dense. Think of it like a city. A young city is spread out and loosely organized, and only over a long time does a packed, towering downtown rise in the middle. In the language of cosmology, that downtown density is called concentration. High concentration means a steep pile of mass crammed into the core, and concentration, the model says, is a kind of clock. It records how long a cluster has been quietly settling, relaxing, and pulling itself tight. A cluster we see at cosmic noon has only had about 3 billion years to do that work. It should still be sprawling and unfinished, with a soft, low-concentration center. Give a cluster the full age of the universe, and its core can climb to a high concentration. Give it only 3 billion years, and it should barely have begun. The number is meant to be small this early. That is not a loose suggestion. It comes straight out of the simulations. A young structure caught mid-assembly should not have a hard, dense, grown-up core. Everything about the standard story says so, which is exactly what makes what came next so hard to explain. In August of 2024, the James Webb Space Telescope turned its near-infrared camera toward the cluster and took images in 4 different infrared filters. Infrared matters here for a simple reason. The expansion of the universe stretches light as it travels, dragging it toward redder and longer wavelengths. Light from something 10 billion light-years away arrives, stretched out of the visible range entirely, into the infrared, which is precisely the light Webb's 6.5-meter mirror was built to catch. When the images came back, there was something wrapped around the central galaxy. Thin, curved arcs of blue-grey light, bending around the cluster's core like reflections in the base of a wine glass. Here is the thing to understand about those arcs. They are not galaxies in the cluster. They look like galaxies, but they are not. They are the smeared, stretched, magnified images of far more distant galaxies sitting far behind the cluster, their light bent on its way to us by the cluster's gravity. This is strong gravitational lensing, the effect Einstein predicted more than a century ago. Mass warps space, and light following that warped space gets bent, the way a lens bends a beam. The arcs are single background galaxies, pulled into ribbons by the mass in the foreground. The light forming them began its journey more than 12 billion years ago. This is not a fringe idea or a trick of the image. Light bending around mass is the same effect that made Einstein famous in 1919. When astronomers watched the stars beside the eclipsed sun shift position, exactly as his theory of gravity said they must. A galaxy cluster does the same thing on a colossal scale, which is why astronomers sometimes call a lensing cluster a natural telescope. Its gravity magnifies whatever sits behind it. But a natural telescope is also a natural scale. The exact curve of each arc depends on how much mass is bending it and how tightly that mass is gathered. The cluster had just handed us a scale. All we had to do was read it. The first result was a record. A team led by Kyle Finner at the Infrared Processing Center (IPAC) at the California Institute of Technology confirmed that this is now the most distant galaxy cluster ever caught, producing strong lensing arcs, the most distant natural lens of its kind we have ever found. On its own, a record is just a record, but this one carries a sting. To bend light into arcs like these, a cluster needs a steep, concentrated pile of mass in its center. A soft, spread-out cluster does not make sharp arcs. So the very fact that this cluster lenses at all this early is telling us its core is already dense. The standard story says the machinery for a natural lens this strong should take many more billions of years to assemble. Here it was, fully working, at cosmic noon. Stop and sit with that for a moment. A gravitational lens is not a subtle thing. To smear a background galaxy into a bright arc, you need a genuinely steep mountain of mass, sharply peaked in the middle. Soft, young, still-gathering clusters simply do not do it. The universe had somehow finished building the lens before. By every rule we had, it should have poured the foundation. And the record was only the doorway, because once the team had those arcs, they could do something more precise than say it looks dense. They could weigh the core. They could put a number on exactly how much mass was hiding in the middle of this thing. And that number is where the real trouble started. To weigh the center, the team fit the arcs to a standard template for how dark matter piles up in a cluster. The profile named for the astronomers, Navarro, Frank, and White. Out of that fit came a single number, the concentration of the inner region, roughly the innermost 100 kiloparsecs. The value was 6.3, give or take about half. That number would be high for any cluster. For one seen at cosmic noon, it is extraordinary. Remember what concentration is supposed to be: a clock, a record of long quiet settling. A 6.3 at this distance is like meeting someone who is 20 years old and finding they already have the settled bones and grey hair of someone who is 80. The calendar and the body disagree, and the disagreement is not small. Then the team did the comparison that turned a surprise into a problem. They took this cluster's concentration and set it against what the standard cosmological simulations predict for a cluster of this mass at this age. Not one simulation, the whole spread of them, the full range of what the model says is possible. And the cluster landed about 3.2 standard deviations above that entire range, outside it. A standard deviation is just a way of measuring how surprising something is. One or two of them, and you shrug. Ordinary scatter, the kind of thing that happens all the time. 3 of them, and you start to sit forward. Past 3, and coincidence becomes a strained excuse. At 3.2, the odds that this is simply a lucky draw from the model fall to less than about 1 in 1,000. This is denser than the standard picture. In its most generous mood, says a structure this old should be able to get. 3.2 standard deviations is not the language of a fluke. It is the language of a signal. Nobody is calling it a broken universe yet. But that number is the kind of thing that, if it holds, means the model is missing an ingredient. And the next question was obvious and unforgiving. Could the measurement itself be wrong? This is where the work gets careful, and where the result stops being easy to dismiss, because the team did not weigh the cluster once. They weighed it 3 separate ways, using 3 different physical effects, and asked whether the answers agreed. The first was the strong lensing, the giant arcs themselves. The second was weak lensing, a subtler thing. Across the whole field behind the cluster, the images of hundreds of faint background galaxies are very slightly stretched, all combed in the same direction by the cluster's gravity, and the statistics of that tiny distortion give an independent measure of the mass. The third was the intracluster light, the faint, diffuse glow of stars that have been torn out of their galaxies and spread through the cluster like a haze, tracing where the mass sits. Strong lensing, weak lensing, stripped starlight. 3 methods that fail in different ways, 3 methods that agree. That agreement is the quiet hammer blow. If the too high concentration were a mistake, a quirk of the arcs, an error in one model, you would expect the 3 methods to disagree, because each of them goes wrong in its own separate way. Instead, they converge. and they agreed with the old measurements too. The mass inside that central region comes to about 65 trillion times the mass of our Sun. The full cluster, counted out to its edge, runs to something like 260 trillion solar masses. Thousands of Milky Ways of material bound into one knot. Years earlier, X-ray and hot gas measurements had estimated a similar mass. Lensing, X-rays, and gas all pointing the same way. The mass is real. The concentration is real. Which means the problem is real. And there is one more detail that makes it stranger. This overbuilt, over-concentrated cluster is, at the very same time, still being built. And picture standing at the edge of it. Not on a world, there is nothing to stand on. But somewhere out among the cluster's outer galaxies, looking in toward the center. Around you, in every direction, the sky is crowded with galaxies. Not the scattered lonely galaxies of the space near us, each one a faint smudge separated from its neighbors by millions of light years, but a swarm, dozens upon dozens of them, whole galaxies close enough to hang in your sky as distinct shapes glowing red with old stars. Between them, gas heated to tens of millions of degrees, so hot it shines in X-rays, filling the space you are floating in with a light you would feel more than see. If you turned your body, you would feel nothing holding you, no ground, no up, no down, only the slow, patient pull toward a center you cannot see. Your eyes would find no edge to the crowd. The galaxies thin out but never quite stop, red and old in every direction, a swarm that formed its stars while the universe was still a newborn. Now look toward the middle. Everything is falling that way. The galaxies, the gas, you. All of it sliding down an invisible slope toward a mass you cannot see but can feel, in the way your path bends. That mass is the dark matter core, and it is packed tighter than anything the universe at this age is supposed to have finished packing. And far behind all of it, threaded through the whole scene, are those thin arcs of bent light. The ghosts of galaxies even farther away, their images stretched into ribbons by the weight you are falling toward. You would be standing inside a structure that grew up too fast, in a cosmos that had not yet had the time to make it, and you would have no way of knowing you were early. Here is the part that should keep you up. This cluster is not alone. Since the James Webb Telescope began its science work in 2022, it has been finding the early universe more built up than anyone expected. Galaxy after galaxy, from the first few 100 million years after the Big Bang, has turned out too bright, too massive, and too chemically evolved for how young it is. Structure keeps showing up early. Every time we look farther back, the universe seems to have already done more of its homework than our models assigned. Record-breaking galaxies keep turning up brighter than the models said the first starlight could ever be. Massive galaxies keep appearing at ages when there should barely have been time to grow them. None of it, on its own, has broken the model. But the misses keep landing on the same side of the ledger. Always too much, too early, never too little, too late. Until now, that tension lived mostly at the scale of single galaxies. What this cluster does is push the same problem all the way up to the largest scale there is. It is one thing for a lone galaxy to form its stars in a hurry. It is another for an entire cluster, hundreds of galaxies and a mountain of dark matter, to assemble a dense, mature, over-concentrated core, 3.2 standard deviations, past what the model allows. That is not one precocious child. That is a whole city, fully built, where there should have been an empty field. The pattern that has been nagging at cosmologists for 4 years just grew to the size of a galaxy cluster, and it is getting harder to look away from. So where does this leave us? Not, it must be said, at the end of cosmology. Being surprised is not the same as being wrong, and a 3.2 standard deviation tension is a signpost, not a demolition. Scientists are careful here, and they should be. There are honest, ordinary explanations still on the table. Maybe dark matter played a larger or earlier role in seeding these structures than the simulations capture. Maybe early collapse is simply faster than the models can yet reproduce. Maybe measuring the concentration of a cluster that is itself still merging introduces a bias that a larger sample will iron out. Each of those is a real possibility, and any one of them could dissolve the tension without touching the foundations of cosmology. That is usually how this goes. An anomaly appears, it sharpens, and most of the time it is explained by something we had not modelled carefully enough, rather than by new physics. And there are less ordinary ideas circulating too. One claim making the rounds ties surprises like this to a study by Lior Shamir, who reported that about 2/3 of 263 galaxies imaged by Webb appear to spin the same way, and suggested it might hint that our whole universe sits inside a black hole. It is a real paper, and it deserves exactly one honest sentence. The lopsided spin may simply be an artifact of our own galaxy's rotation biasing what we see, and it is speculation, not a conclusion. The cluster does not need exotic physics to be a problem. It is a problem in plain sight, measured 3 ways. What it demands is not a wild story, but a missing piece. And the next distant lensing clusters, and the larger surveys coming from Webb and from the Nancy Grace Roman telescope, are what will tell us whether this is a fluke or the first clear crack in a beautiful model. We built a telescope to look back toward the beginning, and we expected to find a universe still under construction, loose, young, unfinished. Instead, 10.4 billion light-years away, we found a structure that was already old. A cluster with a grown-up core in a cosmos too young to have made it. A monster where there should have been a nursery. Maybe the model is only missing a detail, and this all resolves quietly. Or maybe XLSSC 122 is telling us something we have not wanted to hear. That the universe assembled its greatest structures faster and earlier than the story we tell ourselves allows. That gravity in the beginning was not a patient engine at all. The arcs are still out there, bending light that left before the sun was born, tracing the outline of something we do not fully understand. And the record for the most distant lens like this will fall, the way every record here eventually does. When it does, we will be right back at this same uneasy question, staring at another structure that grew up too fast, wondering what our beautiful model forgot. Thanks for watching, and I'll see you in the next one.